We're about to dive into a world you can't see, but one you feel every single second of every day. Yeah, it's the world of these invisible forces they hold the coffee in your mug and they hold you in your chair. These are the fundamental rules of chemistry, and honestly, they're absolutely fascinating.
Seriously, just think about it for a second. Wherever you are right now, you're sitting or standing. But why? Why don't the atoms that make up your body just slip right through the atoms of the floor? The answer is one of the most powerful and really one of the most fundamental secrets of the entire universe.
It turns out you're being held up by what you could call invisible architects. It's this incredibly intricate web of fundamental forces, all working at the quantum level, constantly pushing and pulling to create the solid world that we all experience.
So let's start our journey. We're going to zoom way in, from our familiar world right down to the quantum level, so we can really understand this invisible glue that holds all of matter together.
Our first stop is at the molecular level. This is where we get to explore these really subtle handshakes that make different molecules, stick to one another.
All right, first up are what we call van der Waals forces. The best way to think of them is like tiny, fleeting handshakes between molecules. Now, on their own, they're super weak, just temporary electrical attractions. But, and this is the key, when you get billions and billions of them all working together, they become incredibly powerful.
So how does this actually show up in the real world? Well, when you see a gecko just scurrying up a glass wall, that's not magic, it's van der Waals forces. Billions of those tiny little handshakes between its feet and the surface. These forces are also why water flows the way it does, and why the plastics all around us can hold their shape. It's so subtle, but it is literally everywhere.
Okay, next we've got a slightly stronger handshake, the hydrogen bond. This is a special kind of sticky force that happens when a hydrogen atom gets attracted to a nearby atom that's, particularly greedy for electrons, something like oxygen. It's not a full-on chemical bond, but it is absolutely crucial.
And here's why it's just so important. The two strands of your DNA, the actual blueprint for you, they're held together by hydrogen bonds. Just let that sink in for a moment. They have to be strong enough to hold your entire genetic code together, but just weak enough to be unzipped whenever your cells need to read that code and replicate. A so-called weak force is the absolute key to life itself. Wow.
Okay, let's zoom in even deeper. We've seen how molecules stick together, but what's holding the actual atoms inside the molecule? Well, this is what we call the dance of atoms.
And the choreographer of this whole dance? It's electromagnetism. It really just comes down to the simple attraction and repulsion between positive and negative charges. And that is the force that creates the chemical bonds that form every single substance you can possibly imagine.
This whole dance is all about finding stability, right? A positive nucleus is pulling on negative electrons, while at the same time, those electrons are pushing each other away. So to find a stable balance, atoms will share or even trade electrons, creating those powerful links we call chemical bonds. It's this constant push and pull that builds our entire world.
All right, time for our final zoom in. We're going past the electrons, past all that empty space, and we are plunging directly into the tiny, dense nucleus at the very heart of the atom. This is kind of like the inner sanctum, where the most powerful forces in all of nature reside.
So meet the heavyweight champion of the universe, the strong nuclear force. And its name really says it all. The nucleus is packed tight with positively charged protons that, if you just followed the rules of electromagnetism, should fly apart violently. The strong force is what completely overcomes that repulsion and glues them all together. It's unimaginably powerful, but it only works over incredibly tiny distances.
And then you've got its strange counterpart, the weak nuclear force. This one governs radioactive decay. That's the process where subatomic particles can actually transform, changing a neutron into a proton. This is the force that fuels the stars and forges new elements all across the cosmos.
This really puts the power of these forces into perspective. I mean, look at this. If the strong nuclear force is a skyscraper, then electromagnetism is maybe a person standing next to it. And the weak force? It's a speck of dust on the ground. The difference in scale is just colossal, and it's this incredibly precise, delicate balance that keeps our entire universe stable. Okay, so let's zoom all the way back out. We've seen the fundamental forces, but so what? Why does understanding all this stuff actually matter? Well, it's because when you understand the rules of the universe, you can start to use them.
Hey, remember those invisible architects we talked about at the very beginning? Well, by understanding these quantum forces, we get to become the architects. We can design and build things on a molecular level with a precision we never ever thought was possible.
The path forward from here is just so powerful. First, we learn the rules of these forces. Then, we use those rules to predict exactly how molecules are going to behave. And finally, we use that knowledge to start building the future, literally one atom at a time.
And listen, this isn't science fiction. This is happening right now. Scientists are using these rules to design life-saving drugs, building them molecule by molecule to perfectly target a disease. They're creating advanced materials with properties we've only dreamed of. And this knowledge is the very foundation for quantum computing, a technology that is poised to change, well, everything.
So, the floor doesn't collapse beneath you because of a precise, invisible dance of quantum forces. We've taken this incredible journey into the atom and back, and we've seen how these rules build our reality. Now you know the rules, so the final question is, what new worlds can we build with them?